Good day, class. We will be embarking on understanding fundamentals of AC circuits with this week's series of lecture videos. In this lecture, we will try to describe and visualize AC signals in a simple form. We will first examine the analysis of a typical AC circuit and the need to change the approach to it. We will then define phasors and use it to describe AC signals. Let us look at this AC circuit. The circuit has three passive elements: a resistor, an inductor, and a capacitor. The voltage across the resistor is defined as the current I times the resistance R. The voltage across the inductor is the inductance L times the differential of the current I with respect to the time, while the voltage across the capacitor is defined as the inverse of the capacitance C times the integral of the current I with respect to time. The supply voltage is assumed to be a sinusoid Vm cos omega t plus theta. Writing the Kirchhoff's voltage law for this circuit, we get Vs is equal to Vr plus Vl plus Vc. Once we substitute the individual component voltages, we get the following term. To find the current through this circuit, we need to use differential equations if we continue along this path. There needs to be an easier way to solve such a simple AC circuit. The common parameter here is the frequency for all the components, which doesn't change. The phase and amplitude may change according to individual component values. Let us define the phasor representation of a sinusoid. A typical voltage sinusoid is of the form Vm cos omega t plus theta. Here, Vm is the maximum amplitude of the sinusoid, omega equal to 2 pi f is the angular frequency in radians per second, t is the time period, and theta is the phase angle. The frequency is the common parameter for all components in an AC system. Hence, the two parameters that need to be represented are the amplitude and the phase angle. Here, we define the phasor V1 as V1 at an angle of theta. The V1 is the RMS value of the voltage V1 of t. The phasor is represented in the complex plane with the magnitude of V1 and the angle of theta. For the angle theta, the clockwise direction is considered negative and counterclockwise is considered positive. Some of the properties of phasors are that it is a rotating vector rotating at an angular frequency omega of the system, with the length representing the RMS value of the waveform and the angle representing the phase of the waveform. The phasor for a sinusoid is a snapshot of the corresponding rotating vector at t equal to 0 with its RMS values, and the time domain signal is first expressed as a cosine function before its phasor can be described. Let us draw the phasor for these two examples. For the top right one, the RMS value is 141.2 divided by root 2, which is 100, and the phase angle is plus 90 degrees. Thus, we can draw the phasor as follows. For the bottom right one, the time domain signal is expressed as a sine function, so we need to convert it to a cosine function, which gives us 100 cosine 300t minus 60 degrees minus 90 degrees, or 100 cosine 300t minus 150 degrees. The RMS value is 100 divided by root 2 and the phase angle is minus 150 degrees. Thus, we can draw the phasor as follows. Remember to choose the correct direction for the phase angles, that is, positive phase angles is counterclockwise and negative phase angle is clockwise direction. Until now, we have been looking at sinusoids in isolation. By knowing the phase relationships between the voltage and the current in an AC system, it is possible to characterize and identify the system. We will be defining a few terms to understand the phase relationships better. Let us look at the figure on the left. Both the current and the voltage waveforms originate at the same instant on the time axis and complete one cycle at the same instant on the time axis. We can say that the current is in phase with the voltage as there is no phase angle between the two waveforms. Now, for the figure on the right, the voltage waveform has crossed the 0 first and the current waveform is delayed by 30 degrees. When the waveforms complete one cycle, the phase difference between them is still 30 degrees. We can say that the current is out of phase with respect to the voltage, and more specifically, since the current waveform is delayed with respect to the voltage waveform, we can say that the current lags the voltage or that the voltage leads the current. Since we have introduced phasors to describe time domain signals, let us understand phase relationships using phasors. We have these 4 voltage waveforms. Note that all 4 voltage waveforms have the same angular frequency. Waveforms with different frequencies can't be drawn on the same phasor complex plane. Firstly, convert the time domain forms to the corresponding phasor forms. This gives us the following 4 phasors. Drawing them onto the complex plane, we have the following phasor diagram. Now, if we take the voltage V1 as the reference voltage, we can say that V2 leads V1 by 45 degrees, V3 lags V1 by 135 degrees, and V4 lags V1 by 45 degrees. This should give you a good primer in drawing phasors and understanding phase relationships between phasors. We have come to the end of the lecture. In this lecture, we examined the need to visualize AC signals as phasors, understood phasor properties, and identify how to draw phasors and explain the phase relationships between phasors. Thank you.